remember where we left off. We spoke about implicit differentiation. And what's the idea of implicit differentiation is that, let's say we have this equation, x squared plus y squared equal to 25. And if I bother to solve for y, I would obtain a formula of where y equals to some expression involving x. That's the formula I would have obtained. You see, I might not obtain a formula that works globally for the curve, but works. It's a function locally near the point at which I want to calculate the slope of the tangent line. So I have that y of x equal to root of 25, and then after solving, I could have after solving for the function, I can differentiate it, and I get this formula, which if you look at it, which equals to minus x over y. It's given in terms of both x and y. Now, what is implicit differentiation? It's nothing more than figuring out or pretending that you figured out the solution and just working from there. You see, so here I did not go through step one. I pretended that I did. So I just imagine that I have a solution here. Yes, Karolinushka? Yes. I imagine that I have solution here. And because I haven't explicitly written it out, I just write, when I take the derivative, I write y prime. Because there is a function and there is derivative of that function. So here I pretend to carry out this derivative, and then I just solve algebraically, I obtain the same result. Good. And here we went through several examples where we got that exactly. Right? We solved explicitly for the function and took the derivative, or when we bypassed it. So as I mentioned here, let's look at this equation, x cubed plus y cubed equal to 6xy. If I were to solve it, and again, not enough of you, I guess, wanted to know how to do that, but it's a cubic equation, right? So look how ugly this looks. It's pretty long. And that would have been the solution. After, you probably would have obtained it if you, I'm not sure, I imagine that it would take you at this stage with your algebra, maybe a day to obtain this thing, right? After I explain it. But you would imagine you obtain it, and only then you have to take the derivative. That's pretty tedious. What we do instead, we pretend that we have this formula. Here it is. You see this y? It's really, that's the formula. You imagine it? So when I take the derivative, when I don't see the formula explicitly, I'm just using chain rule. Chain rule for y cubed, it's 3y squared, the derivative of y. You understand? Because it's this thing cubed. So I take the derivative of the cube and then multiply by the derivative of the inner function. And I do the same on the other side. It's really x multiplied by some function, this thing. But I don't have the formula, so where I take its derivative, I write y prime. Everybody sees what I do with implicit differentiation is just I pretend that I know the formula and I just carry on the derivative. And that works pretty well. Good? And in some examples, like in this one, it would actually be insanely difficult, if not impossible, to come up with any convenient formula for y in terms of x. But if I imagine that one exists, I can give the derivative in terms of the function and in terms of other expressions involving x. Good? And then we solved a bunch of those problems. Could you please solve problem number D? You see problem number D here? I want you to find the derivative dy dx for problem D using implicit differentiation. And as you do that, let me depart for a few minutes. I'll be back. Solve problem D. Goodbye. I'm back. All right, so let's see. Are you ready for competition? Let's see how fast I can do it. All right, I'm finished, and you? Oh, Christian, you're hiding today, I see. Doesn't seem like your sister is shy at all, but all right. How come it's what negative? No trouble, Christian. That's fine. Nice that you're here in spirit. Very confused about it. So where are you confused exactly? All right, let's begin solving it. Yes, guys? We cannot, it's too long. Right? We want to figure it out quickly. So I said D, right? So here, let's do it very slowly. Take the derivative of the left and take the derivative of the right. What's the derivative of the left? Do you see that x times sine of y, Christian in particular? Do you see that this is a product rule? X times sine of y, it's product rule, because y, there is no y. If we solve this original equation, do you remember what the original equation was? I think it was the same thing equal to 1. So that's an equation. If I could solve it for what y equals to, I'll get some complicated formula. Do you understand, guys? So let's go up to this point. Do you understand that you can get a formula? So for instance, let's pick something where the formula might be easy to get. So suppose that what we have is x times y plus y equal to 1, right? I could easily get the formula because it's x plus 1 multiplied by y equal to 1. And so y is equal to 1 divided by x plus 1. You all see that? If I have this equation, I can easily find the formula for y in terms of x. This equation, I can solve it. It's just there is no y. There is just this expression, this y is 1 over x. So when I do implicit differentiation, I'm trying to find the derivative of this function whose formula is not given to me as I obtained in this solution, right? So here I could have just said y prime equals to -1 over x plus 1 squared. Do you understand, guys? I'm sorry I wrote on the screen. I can write it on the whiteboard. Do you understand what I'm saying? I need you to confirm that you understand the idea of implicit differentiation, right? Implicit differentiation is really trying to solve for the derivative of, say, this y. But this y, I don't have a formula for it. The formula is hidden as a solution to some equation. Do you understand that? Please write y for yes or n for no. So Joshua says no, okay? Hadi says no. There are some people that say no. Okay, let's again clear it and go through the solution one more time. You see my screen, yes? So let's say I ask you find the derivative of the function y equals to 1 over x plus 1. What do? You say dy dx equal to -1 over, you just use your you can use your chain rule. So it's x plus 1 to the power of -1, and by chain rule it will be the -1 drops down, you have -2, and then the derivative of the inside is 1. So it will be -1 x plus 1 squared. Do you understand what I said so far, guys? So those that said no, Hadi or anybody else who said n, and Christian, you didn't say at this moment anything. Do you understand this solution? Okay, so if I said take the derivative of y equals to 1 over x plus 1, nobody has any issues, correct? You can do the derivative. Now, suppose that instead I told you to find the dy dx. So this long sentence, find the derivative of y, can be written dy dx equal to I don't know what, where the function is xy plus y equal to 1. You see? So I do not see here what y equals to, but because the equation is very simple, I can solve. I can say x plus 1 times y equals to 1. And so y actually equals to 1 over x plus 1. I actually go through the extra step of actually obtaining the formula. So there is no y, there is a formula here in terms of x, and I can take the derivative y prime or dy dx. It's -1 over x plus 1 squared. Good? But the equations, they get very complicated. The equations get much more complicated. You agree, guys? This is a simple equation. I could solve it. So first of all, I spend the time solving it. Secondly, so first I spend time solving it. Secondly, I'm worried that when the equations get harder, I will not be able to find to end up with y equals to something, right, in terms of x. So for instance, suppose the equation is x y squared plus x y plus x cubed, right, equal to x. Okay, so here's another equation. I can still solve this equation. It's quadratic. I can figure out how to solve for y. Yes, what would be I can possibly, if x is not 0, I can divide by x, and I say maybe this is y squared plus y plus x squared equal to 1. Maybe I can do that, and then I'm solving the quadratic equation. It's y equal to 1. There are two solutions, plus or minus, two possible functions here. 1 plus or 1 minus, root of 1 minus 4x squared divided by 2. Okay, So I can still obtain a formula here. So implicit differentiation, guys, is just taking the derivative of y, which in this case is given by an equation. You see, I don't have an explicit formula for y in terms of x. You understand? Here, why I call it implicit? Because I do not see an explicit formula of what the function y equals to in this case in terms of x. Here, I can still solve it. So I might initially just solve it and then take the derivative. You're with me? I see eyes moving about, though some of the eyes. So I think, my God, what this guy is talking about. I think I'm making such great sense. And my God, I'm thinking, I'm so proud of myself. I'm making such great sense. And then apparently nothing to be proud of. You don't understand what I'm talking about. Do you understand what I'm talking about? You understand me, fool? No? Where I fail you? So where am I failing your understanding, guys?
I'm just lost. Like, where did you get the? So after you get y prime, right?
Yes.
So where did you get the formula for x, y squared and like equals x?
No, I mean I just pulled it out of my you know, my mind, right? It's just a formula that because you see those are not serious questions. They will actually, the serious questions will be from physics. I can show you serious questions, right? So this is just the idea is this: my function is hidden within an equation. In physics, you see that those things arise naturally. This is not natural equation. If you're confused about where I got equations like this, I just mean some equation captures y. Nothing special about this equation. Nothing of importance.
Oh, okay.
The point is not the equation. The point is the technique. There is no reason. I look at it in the wild, I will not be solving such derivatives. What do I care about them, right? But the technique is what I'm trying to teach here. You understand? So if I have a formula for y equals to something, I can take the derivative. When I don't have the formula, I think I will solve, and then I'll have a formula, and then I'll take the derivative. So there are two problems. First of all, even if I can solve, it takes quite a lot of time to solve, and it becomes very difficult. Right? So it might be very easily you obtain formulas where solving is enormously difficult, right? You cannot figure a formula. And even if you could figure a formula, the formula might be so complicated that you don't like differentiating it. And you might actually figure other ways to deal with it. Yes, Carolina, makes sense? Completely, right? So you understood what I said, you would be able to explain it. That's one thing that many people do not do. I'm surprised by that. You know, explain it to somebody. Explain it to me or to a person that doesn't understand, to your friend. That's how you know you are good at it. If you can explain it and answer those questions, and then you realize, by the way, by their questions, where you fail in your explanation, what you should improve on.
I got a quick question.
Yeah.
I still don't like. So, all right. I understand for the x to the second plus that problem, right? I still don't understand your math to a certain degree.
My math?
Yeah, because I would say the bottom part. How you got, yeah. I still don't see why you got I know that you factor out y again.
By the way, it's equal to 1. I made a mistake in my y. It's not completely right, if that's what you mean. I need to set it to 0. It should be y squared plus y plus x squared minus 1 equal to 0.
Oh, okay.
It's a quadratic equation where the coefficient here is 1. The coefficient here is also 1. And the coefficient c is this expression. Okay, and that's a quadratic equation using those variables. Good.
Yeah.
So that's when I solve it. But you see, solving it's tedious even here. I can pretend that I carry the solution. I pretend that I have the formula and work from there. That's what you do with implicit differentiation. You understand? I write y prime, pretending that I have a formula for it and not actually carry the differentiation. Good? Let's go back to the problem. So you see, guys, if you want to practice those examples, you can stay always after class and we can solve more of them. It's just too little time during the class. I prefer to spend it explaining new material. So we said D, okay? So you see, so here the equation, first of all, is very complicated. Secondly, even if I could solve it, I imagine it would be pretty ugly. So I try to just take the derivative, pretending that I carried out the calculation, pretending I know what is y as a function of x. So when I take the derivative, it's the derivative of 1, it's 0. You remember the question, it's equal to 1, right? It's the left side equal to 1. So when I take the derivative of 1, I get 0. If I take the derivative of the left, I have x sine of some expression, right? Some expression involving only x really. So it's chain rule here. So initially product rule, derivative of x times sine y, it's derivative of x times sine y plus x intact. Derivative of sine y is cosine y times y prime. You agree? Cosine y, y prime. What is it? Because it's sine, known function that has eaten a function. I pretend I know how to differentiate. So I say y prime. That's chain rule. It's very important, guys. Do you understand me to the step? Say y or something that you understand me up to the step. Still following? Y. Okay, come on. I have 28 people here. How many of you are following? Yes, and then we solve y prime, right? Still following. Conceptually, because you see, you will forget about it. You really have to, you see, I do not forget because I feel it, you see, so it makes absolute organic sense to me. It should make organic sense to you. And you know, how do you know if it makes organic sense to you? Explain it to somebody. Bother your mother, bother your dad, bother your brothers. You can try to explain it to me if you have nobody to talk to. That's why I became a teacher. I just needed to talk to somebody, just bother them. And nobody wanted to listen to me, so I have now people that are forced to listen to me. Yeah, that's how it works. It improves my understanding. So that's great, Christian, you see? Great. So where are we, right? So here it's just product rule. And then plus we have another product rule. Derivative of y is y prime, and then multiplied by sine, plus y derivative of sine is cosine. You see, so we have this expression. We move everything that doesn't have a y prime to the right and everything that has a y prime to the left. You see, I underlined it. I can factor a y prime from this red expression. So I have x cosine y plus sine x times y prime equal to everything else moved across the equal sign. And then I simply divide. And I have my y prime. Naturally, because I did not know what y is, the y prime is described not in terms of x, but in terms of x and y. Right? Yes, go ahead, Christian. What's there to continue? This is just the only interest in this question is that we are trying to figure out how the technique works. Okay, so this is just the technique. So usually when you use implicit differentiation, you are interested for specific values of x and y that are known to you, or for theoretical reasons. You understand? You are either interested for theoretical reasons, so you just use it as a jumping step, or for specific points. So you have many other such examples, which I regrettably don't want to cover to this class. You can read it in my notes, or you can talk about it. We can solve together those questions in office hours. Yes? Good. So one question that I want to ask you: do you realize how I was so fast? Why I was so fast? I mean, you take your long winded way, and why am I so quick at it? No, you see, some people say because you have an answer. No, I mean that would be boring. Naturally, you can give me a question and I'll solve it very fast. Yes, I did pretend to know y as a function of x. That's what you were doing also, but why was I so much faster than you are? Well, one obvious reason is that you haven't really done algebra much in school, but there is another reason. No. It's not because I've seen plenty of those. All right. Do you want me to show you my trick? Yes, I heard it from the previous time. That's good, right? You already get a plus. Your grade is increasing. I like when I'm getting compliments, but that's not an explanation. It's because you're a genius, right? It's not an explanation. It's because my mother never loved me, right? That's what I always had to prove myself. So let's see. Do you want me to reveal my dirty tricks? Yes, all right. I'll reveal to you my tricks. Why is it? Because I actually think about it, right? And thinking about it, I realize what something is. And when you realize what something is, you realize better ways to get there. You understand? Which I'm trying to train you to do, right? You're given a problem and you're just kind of hacking at it, right? Hacking at it. I tell you, get out of this place, and you start hammering in the wall. And there is a door next to you. Just open it and leave. Right? So I search for a door to open it. I'm trying to understand where am I located, right? So you are locked in a room. Where are you located? Maybe it's a hospital. So what you should go is maybe call and say that you are not feeling well. Somebody will open the door. Realize where you are. So I cannot explain this technique because for that I'll need to explain to you partial derivatives. It's not hard. It's just it will take us too far astray, but I will show you the trick I'm using, okay? You will not be able to understand why the trick works, but you can see how to apply it at this stage. Okay, if you are interested, Calc 3, I can explain to you why that works. So first, you have to observe the following. So all of my expressions that I had are of the form a function of two variables, x, y equal to 0. So for example, if I have x squared plus y squared equal to 36, I can think of it as x squared plus y squared minus 36 equal to 0. I move everything to the left. You see? Everything is moved to the left. Good. So f of xy is the function of two variables will equal x squared plus y squared minus 36. Now, for b, the function of two variables is x squared plus xy minus y squared minus 4. You see, just move everything to the left, you'll get left equal to 0. You understand? And whatever left is an expression involving two variables, x and y. That's what all those explain. Okay, so what would be for e? What would be f of xy? What would be this equal to for e? Type in the comments quickly. Oh, Christian, my God, what magic! You are here. So you
Yeah,
understand what I
my
asked you
sister
guys?
left.
For E, what is f of xy? You move everything to the left, and that's how you know what's yes. 1 plus sine y minus cosine xy. Fine. Move everything to the left, yes? So here is the procedure. This is the reason I cannot explain it easily because I need to talk about partial derivatives and I have no time to do that. The procedure is this. Take the expression involving, write minus, and then take the expression and treat x as a variable. Imagine that y is 5, so it's a constant, and take the derivative this way. And in the denominator, do the same, but reverse the roles. X is like 5, it's like a number, and you take the derivative as if y is the variable. Let me show you an example, okay? So let's suppose I am solving problem number B, okay? I'll do problem number B this way. So first of all, I know my function on the left, it's x squared plus y squared minus 1 equals 0. So then what I do is I take derivative, I take minus the derivative with respect to x, the derivative with respect, divided by derivative with respect to y. And that means what? The derivative of this expression with respect to x, it's 2x. Again, I don't want you to be confused, right? Y in my original way of solving it, in the way I told you to solve, it's not, there is no y, there is an expression involving x here, right? But when I do this procedure, I treat this as a function and I don't treat as y connecting to x. I imagine it's like x squared plus 5 squared minus 1. So it's really 2x, everything else 0. And on the denominator, I reverse the roles. I imagine maybe that x squared is like 5 squared plus y squared minus 1. Taking the derivative here, I will get 2y. And don't forget this minus that came from here. And the answer is minus x divided by y, similar to what we had before. That would be the same result you would obtain if you carry out the procedure I taught you to use. If you'd like, try to solve problem A. See if you can do problem A this way. Make sure you understood the method I explained. This I haven't explained, which means you have no idea why that works. It makes no sense to you. Oh, Edwin, great that you joined. I'm glad you came to the evening class. How is it going? Sure, sure. Are we ready? Pavel, you look like you're falling asleep. Come on, guys. Exciting things await us. All right, it's taking too long. I mean, come on, I did it in 2 seconds. So let's see how that's done. Let's look at A. So the idea here, again, guys, be careful. Make sure you understood and you don't forget what the idea I explained. Why this works can confuse you. If you see, because here's what I do. I first take the derivative of this expression with respect to x. You see that? I take the derivative with respect to x. So what's the derivative with respect to x? E to the y, I presume it's just a constant, times cosine x. Derivative of cosine x is minus sine x times e to the y. Minus, here I imagine I see x times maybe 5. So the derivative will be, derivative of sine is cosine. And the derivative of the inner expression will simply be y. Here I take the partial derivative with respect to y, in which I presume x is the constant. So the derivative will be of e to the y is e to the y. Cosine is not bothered. This derivative of sine is cosine, and of x times y, x comes out. And then I write minus this expression divided by this expression, and I'm done. You can use it if you write it here, you can use it to check your work, but I want you to use only methods that you understand why they work. Okay. All right, here is your next question, guys. Figure out what's the derivative dy dx of x squared minus 2xy plus y squared equal to minus 10. You see this? Figure that derivative. Yeah, somebody asked me what am I teaching at Brooklyn College next semester in the spring. Surprise, surprise, another 2 sections of calculus, right? Meaningless existence here at Brooklyn College. But if it's online courses, I think I'll be teaching again probability because I literally like it, right? I love probability. Oh. Okay, Muhammad. What do you mean what to do with the minus 10 full? I'm not sure Okay, Alan, interesting. Christian, you got one. A few people got one. Full, what do you mean with the minus 10? I'm not sure. Rachel, is it 1? What do you mean full? What to do with the minus 10?
Was I supposed to move the minus 10 over before I factored it?
Oh, I mean, you can do it. You can, again, I would advise you guys to use the idea that you understand. What the trick, I showed you what I'm doing, right? You can try to do it to check your work if you want to, but you don't have to use it because it's Calc 3. I'm just saying, if you understand more, you can actually figure out better ways to solve it. That's always true. You see, I'm telling you. You see, how do you get good grades in math? You decide that you want to understand it, and then there are very few cases, and it's very simple. You decide that you just try to slog through, then it's difficult. Come on, guys, let's move on. It's don't take too much on it. Okay, James, I think you're solving another question by now. We're solving this one. X squared minus 2xy plus y squared equal to minus 10. So what's the derivative? Doesn't make sense to me. What for? What do you mean doesn't make sense? You see, guys. Some of you, I divide you into. You see, some people, many of you, in fact, right? You do not ask me or do not try to describe. You just say, I don't know. You say, I do not know. But I do not know, it's too broad. I mean, what don't you know, right? Where are you stuck? Can you simplify the problem? What part do you understand? Do you understand the idea that y might be a function of x or not, right? What's the idea of implicit differentiation, yes or no? Where is a person stuck? I need to know.
Well, basically, I factored it to x minus y squared equals minus 10, and that was like what I was trying to say before. Like, I don't get what to do with minus 10.
Okay, then good. Fine, right? So, come on, guys. I want to see if you what's exacto mundo, Alan. Fine.
No, I was responding to.
No, I understand what you did. You said the same thing as full. I noticed what you said.
No, he said he agrees with me, so to speak.
Sorry?
No, I think he also agrees with me. That's what I meant.
Yes, that's great. I know. All right, so I wish more people said that, but there are two people that answered it correctly, Alan and Fu, and that the entire equation makes no sense whatsoever. So you can take the derivative, but you're basically engaged in an exercise of futility. Well, to what extent? Again, does not exist in real numbers. It doesn't mean this equation is meaningless in general. It's meaningless for real numbers, okay? So you could have actually carried out the calculation, and only a few of you did, and you would say y prime is equal to 1. Are you with me, guys? Where's Karolinushka? Karolinushka, are you here? Great. And the rest of you, do you see that y prime, if you carry the calculation, y prime equals to 1, and that answer is wrong because x minus y squared is what this reduces to, equals to minus 10. There is no real number squared that gives you minus 10. So in the context of real numbers, this equation has no solution. So you're differentiating a non-existent function y. Implicit differentiation makes no sense here. Okay, so you're absolutely correct. It's just the way in the text to say it doesn't make sense. I'm kind of a little, vague. You could say there is no. That's how I would say it, not vaguely. There is no real valued y function that satisfies this equation. You see, that's much more sensical, kind of clear, not ambiguous. I think good. But you were thinking wonderfully, two of you. I'm not gonna capture you with implicit differentiation on such things, but you should be aware that in general, your equation, if it's so hard to solve, maybe there is no solution to begin with. Good. There is this thing that it's very deep, and we're not gonna bother with it, and I'm not gonna capture you. And so for this class, you might as well assume that each equation given, you can take the derivative. Okay. And this equation also is meaningful, but not in the context of real numbers. You have imaginary solutions. So there is something called implicit function theorem, and that's a very, very deep theorem, always used in analysis on manifolds. And that tells you that as long as the equation has a solution, so for example, take this equation, right? This equation is hard to solve for an arbitrary x or y, but you can plug in x equal to 1 and y equal to 1/2, and they will solve this equation. So there is x and y, at least two numbers that solve this equation. And if I take the derivative of this expression, pretending that y is the variable, I get -2. At the number 1, 1/2, I'll get that it will be -2, which is not 0. Those two conditions are sufficient to know that there will be a solution y in terms of x somehow, right? So, and it will be differentiable. No matter how horribly difficult the equation is, having the condition that some pairs of numbers satisfy the equation, and this is called partial derivative with respect to y. You don't have to know it, you can forget it afterwards, but that means that I treat x as not a variable, as maybe 5 or some constant number, and I treat, so what is the partial derivative of y at the point 1, 1/2? This means that each x is equal to 1, and y is the variable. So I just plug in 1 instead of x, and y is still the variable. Yes, and then the derivative will be when I take the derivative with respect to y, I plug y equal to 1/2, and I'll get 2. I get -2 because it's not 0. If the derivative at this point is not 0, and there is a solution, then y can be defined as a function of x. Doing the implicit differentiation thingy is not meaningless. Good. There are some more examples, but I want to move on. You see, here is an example where an equation is in terms of x and y. You use implicit differentiation, you plug those values of x and y, you get the slope, and you get that y prime is 1/2, and then you know how to write the equation of the line. Make sense? All right, let's move on to the next topic. Inverse functions. So let's see what's there. Are we behind? Obviously we're behind. When are we not behind? Hopefully we're not a giant behind instead of ahead, right? That's sometimes how it feels like it. You know, have you ever seen this little statue with an S instead of the face? That's pretty much what I hope we are not. So, inverse functions. So if I write f of x equal to 3x plus 6, what's really happening? Again, guys, so many of you are seeing an x, and that's wrong. What you should be seeing is that an input is multiplied by 3 plus 6, right? That's what this is stating. An input is multiplied by 3, and you add 6 to it. So what is the inverse function? It's the undo operation, undo. Right? When you do something incorrectly, then you can always press undo, correct? So how do I undo what was done to x? So what I need to do is, if f of x minus, so f of x minus 6 is 3x. Divide by 3 will give you back x. So the inverse function, I will explain why that's written this way, is x minus 6 over 3. Okay, I subtract 6 and divide by 3. That operation cancels the action of f. Not every function has an undo. So let's consider this situation. So we have a soda machine. And what is a soda machine really, right? You haven't seen one in a while. You haven't been, I suppose. No. Where do you go now? So there will be another lockdown. It already started in many countries. In Austria, there is a lockdown where they're not allowed to move out of the house, which I, of course, send you a video. I'm not sure if you watched it. Right? So, yeah, it's pretty problematic. People have no critical reasoning whatsoever. So here is a soda machine. If I press 1, I get Coca-Cola. If I press 2, I get Pepsi. Press 3, I get water. Press 4, I get Sprite. Mathematically, it's just a black box that transforms the integers 1 through 4 into Coca-Cola, Pepsi, water, and Sprite. Okay? Now, I can depict this machine. Here is the domain set A. Here is what happens. 1 is transformed into Coca-Cola. 2 is transformed to Pepsi. 3 is transformed to water. 4 is transformed to Sprite. Good? What is the inverse operation going to do? It's going to take Coca-Cola and transform it to whatever produced Coca-Cola, right? So that when you run the functions one after the other, you end up with the same thing you started with. So I have 1, C, back to 1. 2, P, back to 2. 3, W, back to 3. You see, not only you are suffering, you can hear the screams of this wretched animal. Can you? Oh, not only can you hear it, but you can see it, I guess. It's trying to escape from its dungeon. But it has to listen to me just like you do, just for 2 hours. Yes? Yes? Meow. Exactly. Your hell is my heaven. Yes. Do it what? Torture the cat again? I'll show you the cat, and now I suppose he is not registered for this class. I'll kick him out. Yeah, he wants to go out, but not before. Okay, okay. The other cat doesn't give me the satisfaction. He doesn't scream as much. He has a lot of dignity. Good. So back to this problem. You understand? I run f and f inverse, and they cancel each other's operations. Good. So I start with 1. I get 1, right? If I start with Coca-Cola, then I first go to 1, and then I get back to Coca-Cola. You see, whatever I start with, when I run the function one after the other, the two functions, blue and then red, or red then blue, I end up with what I started with. Okay, that's what inverses are doing. And of course, let's see about this function, B. Will that have an inverse? Will there be an undo? Look at it. 1 is mapped to Coca-Cola, 2 is mapped to Coca-Cola, 3 to Pepsi, and 4 to Sprite. Will there be an undo for this expression? Okay, Rafid, wonderful. You say no. Do you all see, guys, that the answer is no? Because what's the picture for B? 1 and 2 are mapped to the same thing. So when I start with C, where do I map it? To 1 or to 2? I cannot recover what was the input that produced C. Good. With the others, I can recover them, but not with Coca-Cola. Good.
Like similar to programming, which is my major.
Okay. And so sure, why not? Again, in programming, you use functions. Why not? So this is the definition, guys. So a function f from the set A onto the set B is called invertible if there exists an inverse function from B to A that undoes the action of f. So that if you run them consecutively, you get what you started with. So what is this x here? Okay, so back again to the Coca-Cola idea. So if I first start with f inverse and then with f, then that means for this example, I start from here. Let's say I start with Pepsi, and then I run first f inverse and then f, and I end up again with Pepsi. You understand? So when I say I start with x and I end with x, whatever I start with at the beginning of the process of running one function after the other, in this case red then blue, I end up with what I started. Understood? Yes? I'm explaining something that you know from school. Yes, guys, it's a prerequisite, but just hopefully that makes sense. Now, similarly, if I start with if I start with f and then go f inverse, doesn't matter if I start here or here. I always end up with it, but the nature of this x might be different. Okay, the nature of the, let's say f then f inverse, the nature of the x is that it's an integer. If I first start blue and then red, the nature is integer. If I start red then blue, then the nature of this x is actually a beverage can. Good. So a lot of people make the following mistake. They say that the inverse function of x is 1 over f of x. The reason is that they don't understand the meaning of this -1 symbol. So look at it. The inverse function for 3x plus 6 was x minus 6 over 3, not 1 over 3x plus 6. What's the reason to use this symbol? Well, there is some analogy to multiplication. So when you have 2 to the power 5, it's 2 multiplied by itself 5 times. And what we can create the same type of notation for composition of functions, for how many times we apply the function to the input. So suppose the function is this. The input, you add 2 to it. So whatever is the input, the function adds 2 to it. Make sense? So f0 means apply the f0 times 2x. That means that you don't do anything. You just keep x, right? f1 of x means apply f1s to the input. You will get x plus 2. Good. Now f2 means apply f twice. So that means just this f of x. So that means f applied to x plus 2, which is x plus 2 plus 2. Good. You with me, guys? So it would be x plus 2 multiplied by 2. If you apply f3 times to itself, it will be x plus 3 multiplied by 2, because each time you apply the function to the input, you add 2 to it. You all understand this?
Wait, shouldn't it be, because you're adding 2, right? Shouldn't the next one be like, instead of 3, it's supposed to be 4? If I'm not going crazy.
No, the next one, but it's 5. I skipped.
Oh, okay. Never mind. All right.
I made the next would be 4 times 2, right? Because I added 2 4 times.
Okay.
Okay, so it makes sense. It's just for this function. Compositions are not easy to calculate. In fact, the fractals, have you seen the pictures of fractals that I showed you? They result out of compositions of functions. So yeah, I can show you pictures, right? So they're complicated. Yeah, so for instance, so you understand how complicated compositions are. That's something I have to suffer through very often. So Julia, here, you see this picture? You see this picture, yes, guys? You see this? This picture is generated as a composition of, yes, it's a composition. It's generated from this function. So what you do is you start with, I'll show you maybe on a new sheet. So what happens over there is you begin with this function. F of x equal to x squared minus 1, right? And then you try to predict what happens to certain points, okay? So, for example, what happens to the point 2? If I take f of 2, that would be 2 squared minus 1, which is 3, yes? And then if I plug in, if I take f2 twice, 2 compositions at the point 2, that would be f evaluated at 3, which would be 3 squared minus 1, which would be 8, yes? If I take f3 of 2, that means apply f3 times to 2. That's the same as f applied to 8, which is 8 squared minus 1, and the answer is 63. Yes? Are you following what happens with a particular point 2, right? So I consider a sequence of iterations, 2, 3, etc. Are you following me? Yeah, so this means I'm running 2 through the same function. It eats the 2 again and again and again and again. So what would happen is for the number 2, if you take fn of 2, it will go to infinity. Apply the function again to 2. You see, look at it. This is applied once. This is applied twice, 3 times. You understand? You just apply to the result again and again and again, right? So apply 2 to 3 times means one application, 2 applications, 3 applications. Good. But on the other hand, if you take, let's say, the number 0, so f of 0 is minus 1. F of 2 of 0, which would be f of minus 1, will be minus 1 squared minus 1, which would be 0. So that would cycle. So you have 0 is mapped to 1, 1 to minus 1, I'm sorry, minus 1 is mapped to 0. So they will be cycling, okay? They will be always cycling like this. So 0 does not escape to infinity. 2 escapes to infinity, 0 does not escape to infinity. And you consider the total dynamics of all points, but not only of points on the real number line, you consider imaginary points. Where do they travel? Okay, and the map of their motion is drawn in that picture that I showed you. So composition of functions is very complicated, but at least I can describe certain. So for some functions, like I picked x plus 2, the dynamics are very simple. X plus 2, everything is moving to infinity. Okay, so in general, observe the following. It's true for all functions. If I take f composed with itself n times and compose it with f composed with itself m times, I'll get this power rule, just like I had for integers. Yes? N, m, they are added. So why do I have inverse? Inverse is saying apply the function 1 time less. So f to the minus 1 composed with f to the 1 should be f of minus 1 plus 1, which should be f to the 0, apply it null time. So this means the -1 here means remove one application of 0. You understand? So for example, if I had f of 4, f composed with itself 4 times, and I wrote f inverse f of 4 of x, that means that you're saying apply f one less time. So it would be f of 3x. That's why the notation is the same. Okay, it's for multiplication of numbers. If I say, let's say 2 to the power of -1 multiplied by 2 to the 4, how do I apply by 1 2 less? I would just multiply by 1/2. You see, multiply by 1/2, it annihilates one of the 2's. But that's not how you apply one less for a generic function. Okay, so let's see if you understand it, guys, as quickly as you possibly can. Here is a very simple function. F of x is 3 times x. I want you to tell me what's f of 4x. F composed with itself 4 times. That's what it means. It's not f multiplied by itself 4 times. It's f eats itself 4 times. And then tell me what's b and what's c. Understood? A, b, and c, please, quickly, because we want to move. Come on, guys, a simple question. Compose f with itself 4 times. But the 81 means it's constant. There is an x there, right? What's the role of the x? Mm-hmm. Yeah, okay. You see what I mean, guys? It should have been immediate, right? I mean, I should have had like boom, running cascade of answers.
Wait, I got a question.
Go ahead.
Because I know that you timesing it's basically the power of 3, right? No, it's not it basically is the power. So I did 3 times 3, it's basically the power of 3, right? So I know it's 81, but then I looked, then wait, maybe it's just never mind. Forget about it. Maybe I'm crazy.
You're right, but again, 81. You multiply something else by 3, right? What happens is whatever is the input, you multiply it by 3. That's what this is saying. Put something into the function, it will amplify it by 3, by a factor of 3. Rachel, yes, that's right. All right, so we need to move. I'm gonna answer this so that that's what I mean, guys. This is what you call pre-calculus. So what is f applied twice to x? It's just f that has eaten f, so it's f of 3x, and it multiplies the result by 3, so you have 3 squared, just like James said. But don't forget you have the x, right? So it's whatever the input. This means the input, it's multiplied by 3, then you feed that back into the function, you multiply by 3 once more, and onwards, yes? So f to the 4 is 3 to the 4, or 81, times x. In general, apply f n times to itself, it's going to be 3 to the n times x. So the dynamics here are very easy to understand. Everything that's not 0, every positive number will go to infinity. Every negative number will go to minus infinity, yes? And 0 stays in place. And what do we have here? So for B, we know that the inverse must satisfy this equation. F of f inverse x must equal to x. In other words, the operations run consecutively will undo each other. So what we have is f applied to anything, it's 3 times that anything, and that should equal to x. That means that this anything equals to x over 3. So the inverse is x over 3. You understood how I solved it? I plug something into f that's supposed to cancel them, right? So what f applied to anything is just multiplication by 3. So this expression is f inverse is x over 3. And this means just compose the inverse with itself 3 times, and then you will get compose f with itself, f inverse with itself 3 times. And in this case, the inverse is division by 3. So you divide by 3 times. It's x over 3 cubed. Good? Now, let's see how good you are at calculating inverses. Very quickly, calculate inverse for A. Come on, guys. Very fast. Calculate inverse for A. Okay, Rachel, great. One person got it. Come on, guys. For this equation, should take you 2 seconds. If you solved A, of course, go ahead and solve B and C, and D and E and F. But first, solve A. undo this operation. I'm not sure what's going on with you. So here is how we solved it in school, right? So in school you were taught to do this, I think. Y equal to 5x plus 8. And then they said swap the variable. So it's x equal to 5y plus 8. And then you solve for y. And then you have x minus 8 divided by 5 is y. So that's supposed to be your solution here. Yes? All right, so why that swapping variables worked. Here is the idea, okay? The swapping variables is just a technique, but what's conceptually happening here? It's just very uncomfortable to write f inverse of x. It's just a lot of symbols, so I just call it y, okay? Take f, and if you plug this expression, they cancel each other, so you should get x. Everybody understands that? So this symbol just means something that cancels f. But what does f do to anything it eats? It's like how should I say? It's anti-wolf operation. So the wolf eats it, and this is this riding hood defense. It just pierces the wolf open, and x comes out. So, but what does the digestive system of f do? It multiplies the input by 5 and adds 8. So what we get here is just 5 times y plus 8 equal to x. That swapping the variables nonsense, right? You don't swap anything. It's just you labeled the inner function as y, and you get the input, yes? So then you get that the inverse function is x minus 8 over 5. Please tell me what's the inverse for b. Come on, fast. I only saw, what, 2 or 3 solutions for A. I want to see lots of solutions for B. It should take you a second. X. If you plug the input in here, you get the input back. Yes.
Wait, I'm sorry. I'm still confused. It's basically -1 is the inverse. You're
Yes,
basically doing
f and e minus 1 is just the inverse. It's not 1 over, by no means. And yes, Carolina, you are right. It's just undo, right? So because composition of functions reminds us of exponential powers. If you look at how it works, it obeys many of the same laws. So that's not multiplication, it's function composition. Inverse is more complicated than 1 over. It's how do you undo 1 over x? So let's look at it together. So I will label the undo function as y. So if I feed it into f, then the undo functions together will generate the input, right? F, you plug the undo of it, they annihilate each other, and all that's left is x. But what does f do to its input? It's always 1 over the input. So 1 over y equals to x. I can then simply take reciprocals, and y equals 1 over x. So the function is its own inverse. It's 1 over x. Good?
Oh, okay.
Now do C.
Yes, it's all right. Yeah. I see it now. Yes.
Good. Good. Now do C, guys. Come on, fast. Okay, James, we'll see. Rachel, I see. Come on, guys, fast. All right, so let's suppose we know how to do that. You are correct. Here is what I do. I set y equal to f inverse of x. And then if I feed this y into f, I'll get x. Good? So x equal to 5 over y minus 1, which means that if I, cross multiply, whatever you call it, right? So you have x, well, actually first do x over 5 equal to 1 over y minus 1. And then I take reciprocals, 5 over x equals to y minus 1, and y equals to 5 over x plus 1, or 5 plus x over x, whichever you like to write. Both are correct. Clear? All right. So now solve d and e, please. D is easy, e I think fairly easy as well. Okay, if it is, then what's D? Three root x, okay. So cube root of x, that's right. So solve e. Come on, guys, almost over. Solve e and E and f, and I guess unfortunately we'll call it a day. Well, y must equal to something, right? So what is y equal to? All right, so let's do e. So again, y minus 1 over y plus 1 equal to x. You understand this step, guys? It's the inverse plugged in. It should cancel the function and you get x. Now, you see, I would prefer to remove some instance of the y. So what I think to do is, I would like the numerator to be y plus 1. Do you agree? If it's y plus 1 over y plus 1, I cross out and I get 1. So I write y plus 1 and pay for it by subtracting 2. 1 minus 2 is minus 1. But you understand why I wrote y plus 1? Because then I can distribute denominator to y plus 1 and obtain 1 minus 2 over y plus 1. And look what I have achieved. I used to have 2 instances of y. Now I only have 1 instance of y. Good? So from there on, I have, I'm going to move 2, because there's a minus here, I'm going to move it across the equal sign to get 2 over y plus 1, and I'll move this x here. So 1 minus x is 2 over y plus 1. So then I take reciprocals. Well, I divide by 2 and take reciprocals. Y plus 1 is 2 over 1 minus x. And then y is equal to 2 over 1 minus x minus 1. If I want to combine it, I can write it this way. Good? Yes? You want to solve one more? Or you look very tired? I'm personally rather tired myself. It's very boring as well. So can you solve question number F? And then we'll be finished, okay? So F, and we'll call it a day. All right, so questions about exams are best relegated for office hours. I'll finish with this thing quickly and we'll talk about the exam, okay, Pavel? Whatever questions you have, we'll try to address them in one moment. And anybody else? And Alan, I give more partial credit than I imagine, than I actually think the question deserves.
Thanks very much.
Sure. Okay, Carolina, thank you. We'll see in a moment. So let's look at the solution, guys. You see, you can afterwards do the questions again. It should be very fast you solve this. So again, we have y to the 5 minus 2 over y to the 5 minus 7 equals to x. And I don't like that there are too many y's here. So I see y to the 5 minus 7. I would have liked to see on the numerator y to the 5 minus 7. So I subtract 7 and add 5. Do you see this? Subtract 7 and add 5. Because really I just wanted to have the minus 7 here, but I have a minus 2 here. So I need to add 5 to have the minus 2. And then distributing the denominator to y to the 5 minus 7 and to 5, I get 1 plus 5 over y to the 5 minus 7, and that's x. So then simple algebra, you continue and you get fifth root of 7x minus 2 over x minus 1. That's your inverse. All right, guys, I am stopping the recording. If you have any extra questions, then let me know. Right, we can solve them very quickly. I'm a bit lightheaded. I don't want to stay too long today.